Hi, my name is Matusz and I work as data science engineer at Pygmalios, and I'll talk to you about digital twins of retail stores and how we use and understand them at Pygmalios. So what's actually going on at retail stores? There could be a guy who is looking for the eggs and can't find them. There might be some shoppers in the queue waiting for a long time to be served. There might be a businesswoman who gives up waiting for assistance and leaves the store without being served. Maybe the staff have no customers to serve and are just hanging around with nothing to do. Or there could be some shopping carts blocking the aisle and blocking the traffic in the store. Maybe the number of shoppers inside the store is violating the COVID-19 regulations for social distancing. So when we talk about digital twins in retail stores, what we understand is that is some kind of a virtual representation of these events that happen at the stores in time. And specifically, we are not talking about the individual events. We look at them in a more aggregated sense. We look at patterns instead of individual data points, and we look at aggregated statistics and aggregated data. So in order to create these digital twins of retail stores, we make use of different kinds of IoT sensors. We have sensors that are based on 3D cameras that are mounted on the ceiling. We have sensors that use positioning using Bluetooth beacons, or we have Wi-Fi routers and access points that collect data. And all these technologies come with different trade-offs in terms of accuracy, and also they capture different parts of the events and what's going on at the retail stores. So to give you some examples, one type of data we look at and we collect is the browsing. So we look at the customer routes, the routes that shoppers take when they are visiting the stores, where they dwell, where they hang around, what sections of the store they pass. And we are extracting metrics based on that. We look at the traffic, so how many people visit the store, how many come inside and go outside, and at what times. And we can do this counting very accurately and with a high precision. Then we look at data for demographics. So we are trying to recognize the gender and age distribution of the shoppers and give statistics based on that. And finally, we can look at queues specifically. So we may have some video cameras mounted above queues and see how many people are waiting in a queue, what's the queue length, how long they are waiting, what is the service time for the queues. So basically our digital twins are built on top of these 4 different data types of data. We have the browsing data for the customer routes, we have the traffic data for how many people enter and exit the store and what's the occupancy of the stores. We have data about the gender and age of visitors, the demographic data, and then we have the queue data about the lengths and waiting times in queues. And on top of these digital twins, we built different applications and services. So one crucial one that we have been working on for a long time is our analytics app. So this is an application that gives you insights and lets you look at the metrics within your store. So you can explore metrics such as occupancy or shopping times in the store. You can look at the different time ranges. You can compare different regions of time. You can compare different stores. So it's something like Google Analytics, but taken to a different context, taken to retail stores. The second category of applications that we built based on the digital twins is our real-time applications for real-time support. So to give you an example, we have been working on this kind of traffic light system that signalizes whether customers may enter or should wait before entering the store based on what is the occupancy, how many people are inside the store, and whether it's under the threshold or the regulations for social distancing due to COVID, or whether they should wait and until somebody leaves the store. And we can do this in real time, so we can have these traffic lights over the entrance of the store and signalize when should the customers enter or not. And the final category of applications and tools we built on top of this data is our planning and optimization applications and services. So in this case, we are trying to support actual processes that happen inside the stores, or processes that are going on at the stores, and let the store managers or store owners to plan and optimize these processes based on data, based on the data. So we are looking at specific cases, for instance, planning the staff, planning how many, when should employees come to work, or planning the tasks that should happen inside the stores, when should be some goods filled up, or other examples. And actually I'll talk a bit more about this final category of applications, and I'll take a case that we have been working on recently and we are still working on, and that's staff planning. So staff planning is a task where we want to create this schedule, this employee schedule that looks something like this. So you have a schedule of when should each employee come to work on different days. So we are trying to build this a month in advance, and this schedule kind of says that, okay, this employee should come to work at 8 in the morning and should leave at 5 in the evening, or they have vacation, they have doctors. So the goal is to create this employee schedule, and this is a standard task that happens in most retail stores. The thing that we are trying to bring here is the digital twin data. So we are trying to have the employee schedule actually reflect what is needed in the stores. So we want to be able to come as close as we can to the headcount that is needed for the number of shoppers, or for the traffic in the store, for the number of transactions that happen. And that's why digital twins are useful here. Using digital twins and the data we are trying to predict the needed headcount in the store, and then trying to find the schedule that best fits the predictions. So to give you an idea of the whole process around generating these schedules, well, first we start with our data. We start with the historical data for the traffic, for how many people are visiting the stores, what's the occupancy. We may use transactional data from the past, and we can look at the service times for customers, and we use this data to predict what is the need for the headcount for the staff for the next month. So we are predicting a month in advance what would be the best headcount for each 15 minutes slot for each day of the month. And then we combine these predictions with information about how many employees are there, what are their restrictions, what is their availability, when do they have vacations, doctor appointments, stuff like that, and also with rules about how should employee schedules be constructed. So maybe rules about that when somebody is working one day, the next day, well, there has to be a gap between the end and start of his shift the next day, or the duration of the maximal duration of working shift. So we take these three sets of data: the staff need, the employee availability, and the workforce rules, and we apply a constraint solver. I'll explain later what this means, but we have a solver that takes this model of the problem and kind of produces the schedule to best fit the need or the constraints. But of course, this is not the final schedule, so this schedule is being adapted by the end users, by the store managers, and it's changed over time. Also, as the month goes on, there could be some unexpected events. Somebody has to take a day off, so the schedule is adapted, and we support this. And then we also look at what kind of changes the store managers did to adapt the schedule, and we're trying to learn from these changes and take them into consideration when we build the schedules for the next month. So we're trying to learn from their preferences of the store managers. So I mentioned this constraint solver. So constraint optimization is kind of the general problem area that we work with and we deal with. And in this problem, in this task, what you do is you model the problem using variables, using constraints, and using objectives. So variables are basically like states. You can have a variable that says, okay, this employee should work on Monday from 9 to 9:15. So that's like a Boolean variable. Yeah, he should be at work, he should not be at work. Then you have constraints that work with these variables and kind of provide rules about which variables can be and cannot be like activated at in different scenarios. And constraints can be hard and they can be soft. So hard constraints are for instance some workforce rules that state that you should have gaps between work shifts. How long should the gaps be, or maybe some rules about what's the fair distribution of morning shifts across employees in the store. And then you can have soft constraints, and soft constraints are objectives. So these are our optimization goals. So we are trying to come as close as we can to these goals, but of course we might not fulfill them. But these are, for instance, how well we reflect the needed headcount or the predicted headcount for the store at each time. We are trying to optimize to get to that number as close as we can. And so when we have this model of the problem, we apply this solver. We push this model to the solver, and its job is kind of to identify the feasible and ideally optimal solutions out of a very large set of candidates. And basically the solver is kind of a black box. So our input is into the model. We can tune the problem model. We don't have access to the solver, or in our case we don't mess with the solver. We optimize the model. So on the right side, to give you just some idea of how this works in practice, or how it's defined in practice, we have one problem that's defined here. So we are trying to maximize 2x plus 2y plus 3z, and we have some constraints. So in the first table you can see these are the hard constraints. For instance, 3x minus 5y plus 7z is less than or equal 45. This is a hard constraint that the solver has to satisfy. And then under that we have the definition of variables x, y, z. And the soft constraint in this case, or the optimization goal, is to maximize 2x plus 2y plus 3z. And under that I have an example of how this would be implemented in the framework that we use. So the framework is Google OR Tools. And so in this framework you would kind of write the Python code that you would define the variables, their lower and upper bounds. You would add the constraints using these inequalities, and then you would set the optimization goal by maximizing the final equation. Okay, so what we discovered is that user interaction is kind of key in this problem. So schedules are kind of like living things. They change. They are adapted. They also the store managers have different traditions of how they solve different edge cases. So they need to be able to easily and quickly adapt the schedule. So the way we think about this is that our solver kind of produces the suggestion. So we produce a suggestion of how this schedule can look like, and this is then iterated over by the user, and we take the user feedback, the changes that they made, and try to improve our optimization in the future based on them. So the benefits that the system provides, well, it saves time for store managers who don't have to do this manually. It improves the operational performance by trying to reflect the needed headcount. That can lead to the better customer service, lower waiting times, better experience for the customers and employees, and in turn result in better revenues. Okay, so what we learned from in this task? Well, we learned that the digital twins and the data is a key part, but it's just one part of the puzzle. So we also have to be able to model the domain. In our case, the domain is quite expressive. We have to be able to model the workforce rules, the preferences of employees. We also have to be able to get feedback from the users and let them interact with the schedule. So this combination of the models, the digital twins, the domain models, and the end user changes is what allows us to find the correct solution. We also learned that store managers have different traditions in how they want to address the problem, and so we have to find the right trade-off between how flexible should we be towards changes from the managers, and also we'll try to find the common ground for all the stores. And also one thought, there is more to AI than machine learning. So constraint optimization is quite a powerful tool, and it provides you with expressiveness and dependability that you might not be able to get with machine learning. But also it comes with its own challenges. It's kind of a black box, and there is a learning curve that you have to climb. But for the right job, if you find the right job, it's the right tool. All right, so wrapping up. So how do we see digital twins at Pygmalios? Well, they provide insights into what's going on at stores. So that's one of the benefits, a crucial one for us. We can understand, and our clients can understand, the behavior of shoppers, how it changes over time. But they're also an enabler for supporting processes that are ongoing at stores. For instance, the occupancy regulation, management of the queue, staff planning, task scheduling, setting opening hours. So we think that a lot of value can come by using the digital twins to and integrating them into the domain, into the challenges that are being addressed, that the people are dealing with at the stores. The challenges that we deal with, we of course, one of the key challenges is ensuring the quality of the sensor data, and this is a topic for another talk, but we have a system built around monitoring data, and we're still improving it. Another challenge is the actionability. So there is lots of interesting insights you can gain from the data, but only some of them are actionable. And our users are busy. We have to be able to find the actionable insights. We also learned that the domain knowledge is important. Data is not enough. We also have to combine data and domain knowledge, and because you can't explain everything from the data, and there is lots of processes that are happening around retail stores that you need to be able to consider. And finally, privacy and ethical guidelines are a crucial challenge for us. So it's a priority for us. We have in-house experts that are working in a team, trying to address them and fulfill them as best as we can. Okay, so thank you for your attention.